I have so I've posted the two recordings from the previous 211 or 361 classes. I am in the middle of recording homework sets for like the solutions to your previous homework set for 361. I have about half of it done. I have to do the rest. Um, I haven't seen these problems before. I didn't write these problems, so I'm having to like figure them out on the fly along with you all. Isa, could you send me the homework set? Actually, if you could right now, if you don't mind, send me the homework set posted for this week.
Yeah, yeah, I can do that.
Um, because that will make sure that I'm like teaching the right things.
Of course.
Yeah, so Sandra, if somebody could send me like photos of those pages from the book, because I don't have your textbook. Um,
Well, one of them is like the first one is its own, but then 78 through 87 is just almost just one problem.
one problem.
It's
Okay.
weird.
Yeah, yeah. I just want to make sure I'm doing the right things with you all. Um,
Yeah, I'll take pictures of those and then email them to you.
okay. Thanks, Isa. And hi, Isa sisters, brothers, kids in the background. Um, so I want to now kind of since we had a bit of an interlude, I want to remind you all of what we had just done, um, and kind of frame that in a way that makes it easy for us to go to what we're doing next. And as always, like while we're doing this, if you have any questions, please type them in chat. They really help me um, know what to do with you all. And if you have any like feedback for me to do the class better, let me know. And even if it's small things like the way I use my tablet, let me know because they will help me help you all better in this kind of disrupted time. So where have we come from? Well, what we saw from before, just a reminder, is that so the time independent Schrodinger equation, um, which tells you psi. Whoops, my tablet has gone weird. Psi of x for constant energy. Have you all used the word eigenvalue in class at all? So, write it up here. Because it's used in the notes. Okay, so let me. I will talk about how eigenvalues apply to this in a moment. So this is the you'll see this acronym. This is the time independent Schrodinger equation. You saw that. So the thing that tells us what size. Yeah, James, thank you for that. I will come back to how eigenvalues matter in a bit because it's actually really core to what you'll do in your advanced quantum mechanics class. So it's minus h bar squared over 2m. Um, uh, Let me write it this way. Well, plus the potential of x times psi of x equals whatever the energy is times psi of x. So here's where we got before for the time independent Schrodinger equation. And then we saw um, in regions where v of x is constant, which is all we're going to look at, um, we saw that psi of x looks like a plane wave. So a plane wave, if you remember, is psi of x equals some amplitude times e to the minus, well, not minus here, e to the ikx e to the minus I omega t. So we've got the time-dependent part and the position-dependent part. So that's something that depends on both. We saw that the wave number k is square root 2me minus v over h bar, and we saw that the frequency omega is simply the energy over h bar. We also saw that in regions where E is less than V, so this piece here, this piece that I'm highlighting, you can, well, actually, let me just highlight, come on. So this here, this is the kinetic energy, right? The total energy minus the potential. Thank you, Isa. Thank you so much. So if the energy is less than the potential, this is the classically forbidden region. Let me get my keyboard out of the way so I can use my tablet a little bit better. Normally you're not allowed to go into places since the kinetic energy is negative, since the kinetic energy is less than 0. But in quantum mechanics, this just gives us an imaginary wave number. So, and we use a notation for this just to make it easier to keep track of the factors of I. So if k equals square root 2m e minus v over h bar, and e is less than v, we can define kappa as just the imaginary part of that. Just to make kappa real. So we can keep track of which things are growing or decaying exponentials. So you all wanted to talk about eigenvalues, and they're used in the notes. So an eigenvalue is I'm not sure of how much Jack wants me to go into like the operator way of thinking about quantum mechanics. Oh, heck, I will. So in linear algebra, so this is going to be a bit of a digression. It's in the notes. You had a question on the homework about it. Okay. Thanks, Isa. Let me actually give me one moment. I'm going to look at what the homework says. Here we go. Thank you. Yes, and I saw your other note in the email, Isa. Thank you. I'm looking sideways at this. Which one references eigenvalues? I'm not quite seeing it. Oh, 68. It's in the other picture. I'm sorry. To describe a matter wave, does the function such and such have a well-defined energy? I see what you're saying. Um, that's an interesting question. So a well-defined energy is related to the eigenvalues. Okay, because the problem doesn't use the word eigenvalue. So what is that? So in linear algebra, um, you all will take linear algebra. Um, we'll put it this way. X, well, V is an eigenvector of the matrix M, and I'm going to write this with two little arrows to indicate that it's a matrix. And lambda is its eigenvalue if um, V times the matrix M equals lambda times the matrix M. So this is a funny relationship, right? Because we know we can multiply a vector by a matrix. We know we can also multiply so a vector times a matrix. Whoops, not lambda times M, lambda times V. Um, so a vector times a matrix gives you a vector. Actually, I think this multiplication canonically goes the other way. Doesn't matter that much. So I can multiply a vector times a matrix and get a vector back. I can multiply a number by a matrix and get a vector back. So in some sense, eigenvectors are they are special vectors where when I multiply them by a matrix, I get a multiple of the vector back. So they're kind of characteristic vectors that don't change direction, they just change magnitude when multiplied by a matrix. I know some of you may not have taken linear algebra, so that may be a little bit funny, but now let's talk about how this applies to quantum mechanics. Um, have you all used the term operator at all in quantum mechanics? Okay, let me write this out and then I will talk about it. So here, rather than having vectors, we have wave functions. So a wave function you can call a state. Um, so psi is an eigenstate. Is that m equals lambda? Um, it is m equals so you can't cancel the v on both sides, Yanju, because the dividing by a vector is not like a well-defined thing. Like, I can multiply two vectors together, but then I get like a scalar if I do the dot product. So it looks like, yeah, you could just divide by v and get lambda back. And in some sense it is, because the eigenvalues lambda, there will be many of them because there may be multiple eigenvectors. Those eigenvalues, in some sense, that set of numbers characterizes the matrix M. But so they are, yes, they're numbers that are very special to the matrix, but you can't have a number equaling a matrix. Um, because what we mean when we say multiply in linear algebra is kind of special depending on what things get multiplied. So in quantum mechanics, psi is an eigenstate of um, an operator O um, if, and this is going to look the same way, the operator acting on, acting on psi equals some eigenvalue multiplied by psi. So we've seen this before, right? We have seen, so examples of operators. Operator here has a dual meaning. Um, so there are two meanings. One meaning is a mathematical operation, usually involving derivatives. But the other can also mean a physical quantity. Have you all done this in class, or is this new material for you? New. Okay, good. This again, I'm not super sure if this is part of the mainline curriculum in 361 or if you wait until advanced quantum mechanics to do it, but it's helpful to see. So let's look at the Schrodinger equation. Let's write down the time independent Schrodinger equation. So um, so let me actually tell you a few of these operators so far. Um, the momentum operator is, and we write operators with little hats above them. So the momentum operator is, let me make sure I get this right. It is I times h bar derivative with respect to space. And you know that kinetic energy is 1/2 mv squared classically, but that's also p squared over 2m. So you might then be able to deduce that the kinetic energy operator is k hat is, I'll write it this way, 1 over 2m times applying the momentum operator times applying the momentum operator again, right? That's p squared over 2m. Well, the momentum operator squared, the i's turn into a minus 1. So that's going to give us minus h bar squared over 2m times a second derivative. Right? So this combination of derivatives, it appears in the Schrodinger equation, but it represents kinetic energy. So when I write down the time-independent Schrodinger equation up here, which I'm just going to copy down one more time, so this is, so I'm going to color code all of the interesting bits, minus h bar squared over 2m partial with respect to x squared times psi of x plus v of x psi of x equals the energy times psi of x. So this is the familiar equation you've been working with for a very long time, right? But you recognize now that we've had our discussion about eigenvalues, what is that? What is that group of symbols? Actually, it's
K-hat.
K-hat. Yes, exactly. So this is K-hat, as Isa said. So what is then all of the left-hand stuff? So now let's rewrite this. I'm just going to undistribute the left-hand side. So this is going to be minus h bar squared over 2m second derivative plus v of x times psi of x equals e times psi of x. What now, if that's the kinetic energy, what is this? Yeah, so it's something called the Hamiltonian, Matthew. What is a Hamiltonian? Or has Jack talked about Hamiltonians at all? No. Okay. This is the crux of quantum mechanics. So we're going to get ahead because you all are a super smart class. I was bragging my head off to Eric Schiff, our department chair, in our faculty meeting yesterday about just how delightful of a class you all are to work with. I see that all 17 of you are here. Like this has been so much fun working with you all in this class, even though I was kind of dropped in the middle of it and I'm not prepared. You all are a super bright class of students, and I'm really excited to see what you all get into in the future, like what you all do in the rest of your academic careers. But what we're about to do now is the transition point between the way that you look at quantum mechanics in this class and the way that you look at quantum mechanics uh, in a more advanced sort of framing. So, Matthew, what is a Hamiltonian? Where have you encountered that term before? Classical mechanics. Yeah, exactly. The classical mechanic, in classical mechanics, um, the Hamiltonian H is just um, kinetic energy plus potential energy. So it's the same in quantum mechanics. That is an operator that represents kinetic energy plus potential energy. So in a way, um, so this is the total energy formula. So the time-independent Schrodinger equation, it becomes H operator acting on psi of x equals the total energy multiplied by psi of x. And this is, in a sense, an eigenvalue equation from quantum mechanics, right? H here, this is like it's like a matrix. So remember a matrix, I can spell. Come on, eraser. A matrix times a vector equals a vector. Psi here is playing the role of the vector. This is called a state vector. It just tells you where the particle is, right? Actually, I should write these as functions of both position and time. So this is not the time-independent Schrodinger equation. This is the full Schrodinger equation. So psi is a state vector, and then E is actually, yeah. This is the energy. This is just a number, right? It's not a vector, it's not a matrix, it's not an operator. And this is the eigenvalue in the eigenvalue equation. And psi there is the state vector again. So this Schrodinger equation that you've been looking at this whole time is really an eigenvalue equation, where the vectors that you're thinking about are actually infinite dimensional, right? It's psi as a function of every position x, but that's okay. We can think about linear algebra in infinite dimensions. That's cool. One sec, I need to do something for the physics clinic. The physics clinic opens at 1 and they need me to do something for them. Stand by for 2 seconds, folks. I am so sorry. All right, that's done. So yes, you can still go to the physics clinic. The physics clinic, let me get you the URL. The only way I know to get it is off of my website, but I am so sorry, folks. Like we had made this announcement to Physics 211. I thought there was a broader announcement that went out to everyone. I will send this out to everybody. Remind me if I don't. But that link goes to the Zoom meeting that is the physics clinic. There are 3 TAs or 2 TAs in there right now, Manu Manitil and Meryl Asp, who are answering questions of anybody who drops by. I'll be there tomorrow morning from 8 to 10. So the Schrodinger equation then is just an eigenvalue equation, where instead of matrices, we have these operators. Instead of vectors, we have wave functions. So remember, this was from my very first day teaching you all. We proposed that well, we saw that we would separate psi of x and t into one piece that depends on x and then another piece that depends on t. This really is the time-independent Schrodinger equation. And we saw that psi of t equals e to the I energy times t over h bar. Remember when we did that in the way back beginning? It turns out that the full Schrodinger equation, I wasn't quite expecting to go here, so I hadn't even thought about this morning. So I apologize if I'm a little scattered. The full Schrodinger equation, including the time parts, is that the Hamiltonian operator acting on psi of x and t equals give me 1 second. I want to make sure I get a minus sign right. Yes, it is plus I h bar time derivative of psi of x and t. So one way to think of the role of the Hamiltonian is it's a thing related to evolution in time, right? But then, so let's think about how we make this an eigenvalue equation, right? What we did, so remember way back before, we said, think back to the first day when I was teaching. Let's imagine states where this separates equals a position part times, I think we actually use phi for that. Yeah, phi is the correct letter in this class. I remember seeing that in Jack's notes. So I'll correct it up top. What we're really doing is we're trying to find which states are eigenstates, eigenvectors of the Hamiltonian. So let's now put this in. So if what we have now is h psi of x phi of t equals I h bar derivative with respect to time of psi of x phi of t, we observe two things, right? Sorry, I just got a text from Jack. Jack says he is doing better and wants me to tell you. So if you have any messages for Jack, please type them in. He's on text with me now. I'm typing all of your messages back to him. I'm telling him about the haikus. Um, so we'll observe that Jack says lol to all of those comments. We observe that the Hamiltonian, since the Hamiltonian doesn't depend on time, this acts only on the spatial part, right? Because the space derivatives in the Hamiltonian don't affect phi of t. And this piece acts only there. So really what you wind up with, so again, we're taking the full Schrodinger equation and we're now looking at it again in the operator way of thinking about quantum mechanics. So this gives us, I'm going to go on down to the next page. H is going to turn blue here because it's a thing that acts on position. So this is H psi of x times phi of t equals psi of x times IH derivative with respect to t phi of t. Well, what's really happening here, right, is we know that phi of t, we figured out earlier that this is e to the IET over h bar minus IET over h bar. So when you take derivatives of that, right, the energy comes down. Canceling out that thing over in the front. And what this really gives us, note here that the derivative of phi of t equals minus IE over h bar t, or phi. This turns the Schrodinger equation into this. H psi of x times phi of t equals, so the minus I over h bar cancels the I times h bar, because remember 1 over I is just minus I. So this gives us E times this times psi of x. So before, what we said was solve the Schrodinger equation to find stationary states. So all those things that we did in solving the infinite square well, we saw that the stationary states look like this, sines and cosines, sine n pi x over L. Those were the stationary states. But now that we're talking about eigenvalues and Hamiltonians and things like that, we recognize that stationary states are the eigenvectors of the Hamiltonian operator, which was minus h bar squared over 2m second derivative with respect to psi plus v of x, and their eigenvalues are their energies. So we've got kind of two ways in our mind to look at the Schrodinger equation. One of them using this old way where we just sort of said, here it is, and this new one where we say, actually, the reason it's that way is because we know the form of the Hamiltonian, because the Hamiltonian is just the operator for kinetic energy plus the potential energy. So was that super confusing to everybody, or did this make some sense? Is there anything about that you want me to clarify? Okay, Isa, this topic really, like, it belongs to the upper level quantum mechanics class, and I've thrown some math at you that you haven't seen before about like eigenvectors and this language. Really, what I want, my learning objective here for you all in talking about this is for you to, yeah, James, that's kind of what I was expecting. For you to recognize the Schrodinger equation when you see it as really just an energy operator multiplied by the wave function equals the energy number times the wave function. So you can think of this thing here. Whoops. This thing here is really the total energy, where we've written the kinetic energy in a funny way. Yeah, so linear algebra makes no sense when you take it as a physics major, because it really makes sense when you start applying these things to solve quantum mechanics. Yeah, I had this same experience, Paul. I got an A in linear algebra. I have no idea how I got that A. I didn't learn anything. I didn't understand what any of it was for until I got to senior level quantum mechanics. And then, like, when you get there, you'll start doing, like, diagonalizing matrices and doing stuff like that for actual matrices representing quantum mechanical things, and then it'll start to make sense. But what I want you to see is I want you to see that framing of the Schrodinger equation. This funny mess of derivatives plus potential is really just a total energy, and you can think of it as an operator, as the Hamiltonian operator that says, take a second derivative, multiply it by a thing, multiply by h bar over 2m. Yeah, is anybody else having audio trouble? Okay. Sandra, it may be on your end then. Um, and then when you see this business with eigenvalues, next time you go back to quantum mechanics, it will make a little bit more sense. But the other reason I wanted to talk about that today, and the reason that it's in, um, I think, the notes that Jack gave me, is if, um, and I'll write this out, if the wave function is an eigenvalue of an operator, then that state has a definite excuse me. Sorry for those wearing headsets. I had to sneeze suddenly. Has a definite value of the quantity. So as an example, if psi is an not an eigenvalue, an eigenvector, is an eigenvector of the Hamiltonian, which we discussed is the energy operator, um, with eigenvalue E, then, and here's where the probabilistic nature of quantum mechanics comes in, then a measurement of the energy of that state will always be E. So eigenvalues then, or eigenvalues are the numbers that you're guaranteed to get when you measure something. Let's look at an example. So I want to look at plane waves now. And then we'll make a transition to the first thing on our new segment. So consider a plane wave. Psi of x and t equals, so we've got the keep my color scheme from before. I've got the position part, e to the ikx, e to the minus I omega t. So I have an exercise for you all to do. I want you all to do something. So get paper handy. So what I want you to tell me is, I have two questions for you. Is this an eigenvalue of the Hamiltonian operator, which, remember, is minus h bar squared over 2m second derivative with respect to x plus v. V here will be a constant. Sorry, I shouldn't say eigenvalue. This is an eigenstate. And then after you do that, actually before you do that, do the second one first. Is this an eigenstate of the momentum operator, which is IH bar times the first derivative? Crap, my program crashed. I'll be right back. there's some kind of instability in the way this works, and I'll get it sorted. So you go here. I need to share this. Okay. So I'd like you to get it to actually apply these operators to that state and tell me what the momentum and energy are of this plane wave. And what you can do, I will actually, there's no way to keep this and the whiteboard up. I was going to try to fire up a shared whiteboard and let you all work on that. I'll wait a minute for you all to do this. And I'll say a thing, if so, what are the eigenvalues? So please ask if you've got any questions as you do the calculation. My volume is small. Can you hear me better, Yanshu? Okay. I think I knocked my headset crooked when I sneezed. And I'm waiting on you all to work on this calculation and ask questions. So let's do these. So first I look at momentum. So I want to calculate IH bar. Derivative with respect to space of to the ikx e to the minus I omega t. Actually do that in a different color. And you notice that the only thing that's got a spatial piece to take a derivative of is that. So this gives me let's see, taking a derivative pulls down an ik. So this gives me minus k h bar right, times ae to the ikx e to the minus I omega t. So when I took a derivative with respect to psi, so yes, Danielle, exactly. If the output is the original plane wave times a constant, that means it's an eigenstate. So all of this stuff, let me write what these things are. This is the momentum operator on psi of x and t equals a constant times psi of x and t back. Exponential is very nice like this, right? Because when you take derivatives, you just get that constant back. So yes, these things are eigenstates of the momentum operator. Now let's do this one. Well, it's not worth doing. But notice if you look at when you apply the Hamiltonian operator to the wave function and you take two derivatives, that brings down a factor of k squared. Actually, let's do that one. It is worth doing. So here, what I want to write h acting on psi equals, well, I have minus h bar squared over 2m times the second derivative with respect to x of this. So the second derivative with respect to x is going to bring down a k squared times a minus 1, right? Because two derivatives bring two factors of I is a minus 1. Multiplied by that again, times a e to the ikx e to the minus I omega t. And then I'm supposed to take v times that. So plus v a e to the ikx e to the minus I omega t. So you notice again, I've got a whole bunch of stuff multiplied by this. So what is that? This is equal to, so let's just extract all of the stuff out front. Those minus signs cancel, and I get h bar squared over 2m k squared all times oops, forgot the v, plus v all times e to the ikx e to the minus I omega t. So again, you have, yep, exactly. This is the function times a constant. This was our original psi of x and t. So the plane wave is also an eigenstate of energy. Hamiltonian's the energy operator, right? So this here is the energy eigenvalue. So let's do a little bit of reverse engineering. Right? If the energy is h bar squared over 2m k squared plus v, solve for k. One sec, Ista. So if I solve for k, I get k equals the square root of 2m e minus v. Is that right? No, it's not. Yes, no, that's right. 2m e minus v over h bar squared. And hey, look, that's what we had before. So what it means to be an eigenstate of something is that when you apply that operator to a function, you get back that function times a constant. Let's look now at one that's not. So does this calculation make sense to everybody that when we applied both the momentum operator and the Hamiltonian operator to the plane wave function, we always got back a constant multiplied by that wave function again? Yes. So if the physical meaning is that this state has a definite value of that thing. So a plane wave, right? You can think of a plane wave as like, it represents a particle just moving at a constant speed. That has a definite momentum and a definite energy. So what we concluded here was a plane wave has both a definite momentum and a definite energy. But now let's look at the standing wave modes for the simple harmonic oscillator. Doesn't that mean it can't have a definite position? Yes, Isa, exactly. So the position operator is just x. We've seen that the momentum operator is IH bar derivative. The Hamiltonian operator is write it this way. Minus h bar squared over 2m second derivative. The position operator, the operator that tells you the position of something, is just multiplying by x. So if I take x times e to the ikx e to the minus I omega t, x is not a constant, right? X is a thing that is different for different places in space. So this is not equal to a constant times psi of x. So yes, a plane wave is not an eigenstate of position. It turns out very few things are an eigenstate of position. Um, so Isa, I think it will clarify what you're thinking of if we look at an example where something is not an eigenstate of something. Um, so now let's look at the stationary states of the square well. Are they eigenstates of the Hamiltonian and momentum? Question mark. So I'm going to do momentum first. And I'm going to let you all do this one. And Isa, since you asked the question, I'm really interested in what you have to say here. So the momentum operator, remember, is IH bar derivative with respect to position. And the wave function was A sine n pi x over L. So is this wave function an eigenstate of momentum? Scribble this down on your paper and tell me what you get. No. Why not, Nick? Yeah, sine turns into cosine. So P acting on psi of x gives us, well, IH bar n pi a over L cosine n pi x over L. Nope, that's not some constant times psi, right? Yes, Isa, you're amazing. Exactly. So this is not an eigenstate of momentum, but it is an eigenstate of the Hamiltonian. So h psi equals, so v is 0 here. So minus h bar squared over 2m sine n pi x over L. Whoops, I forgot my second derivative. Um, uh, so this gives me, so I take two derivatives of sine. They're going to cancel the minus sign in the front. So this gives me h bar squared over 2m. And then I have the thing inside squared. N squared pi squared over L squared times sine n pi x over L, which means that h psi equals, I'll make it explicit and write the psi of x, equals h bar squared n squared pi squared over 2ml squared psi of x. Does that formula look familiar to anybody? Have you seen that thing in front of psi before? Yes, this was in your homework. Yes, you have, James. What is it? Can't remember where. Yep, this is the energy formula for the bound states of the square well. So, right, what did we just observe? We saw that this stationary state is an eigenstate of the Hamiltonian, and the eigenvalue is the energy. So that's kind of the upshot of the whole thing. And you knew that this wouldn't be an eigenstate of momentum, right? Because the bound states of a infinite square well, you can think of it as the particle bouncing back and forth. So obviously, it's not an eigenstate of the Hamilton of momentum, right? Sometimes the particle is going to the right, and sometimes the particle is going to the left, and that's what it means to be an eigenstate. Or excuse me, sometimes the particle is going to the right, sometimes the particle is going to the left. So since there's not one definite answer for the momentum, it can't be an eigenstate of momentum, right? Sometimes it goes to the right, sometimes it goes to the left. Not one answer for momentum. But it does have a definite energy. That is the energy, the thing that we just calculated. Um, and then when we acted with the Hamiltonian operator on the wave function, we got back that energy multiplied by the wave function. Um, so I want to address a few folks. So Isabella, does this, like these two examples, does this clarify what it means for something to be an eigenstate? Good, good. Um, so Danielle, you observed that if the output is the original plane wave times a constant, um, does that mean that it's an eigenstate? Um, you see kind of how that observation was held in the beginning, but it doesn't hold now. Um, and Yanju, do you see how this connection between the mathematical sense of something being an eigenstate, right? That like when I apply the operator to the thing, I get back the thing times a constant. The connection between that and the state having a definite value, like in the infinite square well, the particle's bouncing back and forth, so it doesn't have a definite momentum, but it does have a definite energy. Good, good. Um, Again, it's harder for me to like see your faces and see if you're following stuff, so I have to ask. So, do you remember the question on your homework? There was one where you had to show that um, for the bound states of the simple harmonic oscillator, um, what you got, they were the superpositions of two plane waves. Do you remember doing this for your homework? You can say no if you don't remember that. Okay, so you don't remember that. So this is a good lead in to what we will do next Tuesday if Jack is not back. And if Jack is back, I imagine this is where he will do it. So I have the solution video. You can look at that. But what you did was you said, okay, psi of x is a sine n pi x over L. And if you remember Euler's formula, remember e to the I theta is cosine theta plus I sine theta. So if I want to solve for, or if I want to imagine what sine theta would be, let me now write this down. So e to the minus I theta is going to be cosine minus theta plus I sine minus theta, right? So now what I'm going to do is I'm going to subtract one of these equations from the other. I'm allowed to do that. So that means that e to the I theta minus e to the minus I theta is, well, this is going to be cosine theta minus cosine minus theta plus I sine theta minus I sine minus theta. Now, does anybody remember any properties like, is there a way to simplify cosine minus theta? Yep, cosine is an even function, is even, so cosine theta equals cosine minus theta, and that term cancels. But is sine even or odd? I'm almost out of time, so I'll just go fast. Sine is odd. So that means that e to the I theta minus e to the minus I theta is 2I sine theta. And then that means that you can say sine theta is e to the I theta minus e to the minus I theta over 2I. And that lets you simplify the thing above. So what you get, right, when you do this, you get that psi of x is, well, it's 1 over 2I multiplied by e to the I n pi x over L minus e to the minus I n pi x over L. So those look like plane waves, right? So that means that the particle in the box really is a combination of a plane wave going to the right, notice that the thing in front of the x is positive, and a plane wave going to the left. And that's where we'll pick up again on Tuesday. Any questions from anybody? I know we kind of got sidetracked talking about eigenvalues and eigenvectors and operators and such. That was a little bit in the notes that I was given, but that idea will super come back in your upper division quantum mechanics class. So today was kind of a little peek at how quantum mechanics is done in a more sophisticated way. Any questions for me? Where will the solution be video posted? It'll be on YouTube. I will, it's the same YouTube channel I'm using for 211. Once I finish it, I will email to you the link. And this lecture will, of course, be posted as well. I just got to finish it. He said it takes time to record. Just like it takes you time to do your homework, it takes me time to do your homework too. Thank you, Matthew. If there's anything more that I can do for any of you, please let me know. I will, Charles. Talk to you later. Aw, thanks, James. Where can you find the video? It will be up on YouTube, so I'm going to stop the recording right now.